At the microscopic scale, the familiar rules of movement seem to break. Particles jitter and bounce in unpredictable directions, driven by constant stochastic noise. This chaos disappears as we zoom out. The macroscopic world operates with a smooth, reliable determinism, where every action has a predictable reaction. Albert Einstein provided the first formal map of this microscopic chaos in 1905. He used a random walk model to describe the mathematical foundations of classical Brownian motion. Jean-Baptiste Perrin later used laboratory experiments to confirm Einstein's work. He demonstrated that at any magnification, a particle's path remains equally jagged and fractal. These discoveries left science with a fractured view of reality. The chaotic subatomic world and the predictable macroscopic world were treated as two disconnected universes with different sets of rules. However, reality rarely respects this binary split. Biological cells and human financial markets often display anomalous diffusion, behavior that is too organized to be random, but too erratic to be classical. The mathematician Benoit Mandelbrot developed fractional Brownian motion to help model these strange middle ground anomalies. This model relies on the Hurst Exponent, a sliding scale measuring randomness from extreme subdiffusion to smooth ballistic movement. While mathematically effective, it lacks a physical cause. In Mandelbrot's model, the exponent is an arbitrary recorded number, not a value derived from physics. The observer-dependent theory of everything, or ODTOE, proposes a physical mechanism to explain these varying levels of order. It suggests that the transition from quantum chaos to classical clockwork is a single continuous spectrum governed by one equation. That equation is h of s equals 1 plus s divided by 2. In this formula, the variable s represents coherence, the degree to which an observer cluster acts in unison. When coherence is at 0, we reach the quantum limit. Stochastic noise is at its maximum, and every movement is purely random. This state of zero coherence aligns with the path integrals described by Richard Feynman. He showed that quantum trajectories are incredibly jagged, with a fractal dimension of 2. At this scale, ODTOE establishes that the time required to move between observation levels increases by the golden ratio. Because diffusive distance is the square root of time, the spatial scaling factor at zero coherence settles at exactly the square root of the golden ratio. This explains why quantum paths and classical Brownian motion share the same fractal structure. At the zero coherence limit, fundamental chaos follows a rigid geometric rule. As coherence rises above 0, the system begins to change. The increasing order starts to suppress the random stochastic noise. This transition is governed by the spiral gap parameter. It defines the specific mathematical ratio between directed drift and random noise as they compete for dominance. We see this struggle in biology. In the crowded interior of a cell, molecules experience subdiffusion, where dense environments limit movement and suppress individual coherence. At a much larger scale, a trending financial market functions because the collective behavior of traders possesses positive coherence, creating a persistent drift that overcomes market noise. Anomalous diffusion records a system in flux, shifting from pure randomness toward directed movement. It is the physical signature of coherence emerging from noise. Eventually, the scale reaches its maximum limit at a coherence value of 1. At this point, stochasticity vanishes. The system becomes fully deterministic and entirely predictable. Macroscopic coherence appears in a Bose-Einstein condensate, where atoms merge into a single quantum state. Acting as one, fractal jaggedness disappears, producing smooth, ballistic motion. In this state of total determinism, the spatial ratio between observation levels reaches the pure golden ratio. Large-scale determinism requires total coherence to eliminate underlying randomness. When every part of a system acts as a single wave, the fractal jaggedness vanishes. By linking the Hurst exponent directly to coherence, ODTOE provides a physical reason for why systems scale the way they do. This framework places the golden ratio at the center of physical movement, mirroring the patterns we already observe in the seeds of a sunflower. While we have traditionally viewed the golden ratio as a tool for aesthetic design or architecture, ODTOE suggests it serves a deeper structural purpose. The ratio acts as a fundamental structural constraint on reality, defining how a system transitions from a jittery quantum state to a smooth classical one. These values provide the two hard limits for any physical process: the square root of the golden ratio for total chaos and the golden ratio itself for total order. The transition between quantum and classical scales is a single continuous trajectory. The mathematics of coherence bridges these two worlds, showing them to be parts of one unified architecture.